You're sitting in a long meeting, or maybe you're just reading the title of this video, and suddenly your jaw drops and you take a massive gulp of air. For centuries, we've assumed this was a simple sign of boredom, a desperate reflex to pull more oxygen into a sluggish system. But that theory fails to account for the timing. We actually begin yawning long before we ever breathe air, with the reflex first appearing during the second trimester of fetal development. In the womb, a yawn serves a specific physiological purpose. The deep stretching motion helps coat premature lungs with a lubricating liquid called surfactant, while the intense contraction of the jaw muscles provides the sensory input required to stimulate early brain growth. We tend to view our adult yawns as a breakdown in focus, yet the fetal data suggests the opposite. This reflex is an ancient developmental routine, essential for the physical construction of our respiratory and nervous systems. The yawn acts as a biological operating system, initializing survival-critical programs months before our first breath. To understand why we carry this program into adulthood, we have to look at how the brain manages heat. Your brain uses up to 40% of your body's metabolic energy, and like any high-performance processor, it generates heat as it works, temperatures that rise even higher during periods of sleep deprivation. When the brain approaches its thermal limits, it triggers the thermoregulatory theory of yawning. In this framework, the yawn functions as a specialized heat exchange cycle designed to protect cortical hardware. This diagram shows the mechanical first step. When you stretch your jaw, the lateral pterygoid muscles contract, acting as a biological pump that squeezes stagnant, hot blood away from the skull. Simultaneously, a deep inhalation draws a volume of ambient air into the nasal and oral cavities. This air passes over a network of blood vessels, cooling them through convection and evaporation. This freshly chilled blood is delivered directly to the forebrain, the area responsible for language and sensory processing, restoring the brain to its optimal operating temperature. Data from the Gallup studies supports this cooling effect. In trials where participants watched others yawn, those with warm packs on their heads caught the yawn 41% of the time, while those using cold packs yawned only 9% of the time. This explains why we stop yawning when it's exceptionally hot outside. If the ambient air matches our body temperature, it loses its cooling utility, and the brain switches to more aggressive measures like sweating or panting. The rapid cooling observed in these studies suggests that yawning is a proactive maintenance cycle, forcing the brain into a more alert state precisely when it starts to overheat. Beyond temperature, fatigue leaves a distinct chemical trail. When we are exhausted or under pressure, our bodies release a stress hormone called cortisol as a warning signal. Research into the Thompson cortisol hypothesis suggests that yawning is a direct sensory reaction to these rising hormone levels. This graph shows how cortisol hits a critical threshold, triggering a yawn that helps the body modulate its internal stress state in real time. To lower those levels, the body utilizes the vagus nerve, a primary neural highway connecting the brainstem to the heart and lungs. The physical force of a deep yawn provides the direct mechanical stimulation this nerve needs to activate. This stimulation engages the parasympathetic nervous system, which triggers a rest and digest state. It's why a yawn is often accompanied by secondary physical signs like watery eyes or a sudden relaxation of the shoulders. The yawn acts as a chemical reset, intercepting a rising tide of stress and forcing the body out of an agitated state. Up to this point, we've looked at the individual, but the most baffling trait is its ability to spread through a group without conscious effort. This is the fascinating work of mirror neurons. These highly specialized brain cells fire both when we perform an action and when we observe someone else doing it. When you see a friend yawn, these neurons effectively simulate the physical experience in your own mind. This social reflex doesn't appear until around age 4, which is the exact developmental window where human empathy and social understanding fully emerge. We see the exact same pattern occurring in other highly social animals. Chimpanzees and domesticated dogs catch yawns at significantly higher rates when they are observing individuals they have an emotional bond with. This suggests that contagious yawning evolved as a synchronization tool. By passing the reflex through the group, the entire pack matches its alertness levels and brain temperatures, helping the collective stay vigilant. Even with these social and thermal benefits, researchers are still uncovering new layers of this reflex, including its role in the brain's deep internal maintenance. This diagram illustrates the fluid dynamics of a yawn. The sudden, deep intake of air creates a pressure shift that causes a downward flow of cerebrospinal fluid through the central nervous system. This sudden movement acts as a literal wash for the nervous system. By forcing this fluid to circulate, the body can more effectively clear out the metabolic waste that accumulates during intense mental activity. By integrating these three functions, like thermal cooling, vital chemical regulation, and social synchronization, the yawn reveals itself as a versatile survival tool. It's a reminder that our smallest involuntary habits are part of a deep biological intelligence. To keep exploring the hidden systems that make you human, subscribe, and we'll see you in the next video.